Good morning. I'd like to talk to you a little bit about some of the work we've done on simulation of sensors. I'm Dr. Mark Law, and I'm working with Research Assistant Professor Aaron Patrick, recent PhD graduate Maddie Shulo, PhD student Thomas Weingartner, and this work was funded by Texas Instruments and the Defense Threat Reduction Agency. So I'd like to talk to you a little bit about the overview of our software and give you a little feel for the capabilities. And then talk about two particular sensor applications, a gallium nitride HEMT sensor and a Hall sensor, and then conclude. So our code is known as Flukes. We usually put a wildcard X in there, the Florida Object-Oriented Simulator, and there are several varieties. We have a process simulator, which is used at Intel and is used for all of their process development for their chipsets. We also have a device simulator, Floods, which we've used not only for 3.5s, but also silicon technology, as you'll hear in the sensors. We've also done reliability floors and looked at how both radiation damage can create long-term failure, as well as breakdown in materials from high fields and tunneling and injection of charge. And finally, our newest research work is FLUS, the Florida Object-Oriented Superconductor Simulator. We've been working on simulating both Josephson junction formation as well as performance and simulating Cooper pair transport through the barrier and how it switches from the superconducting state into the regular state. The code is pretty much commonly shared. The differences are in the startup scripts and the kinds of solution variables that are enabled. All of the partial differential equations are specified in a scripting language, and I'll talk a little bit more about that. We call it Alligator. The code has been commercialized by Synopsys in two versions, Centaurus Process and Centaurus Interconnect are both based on our code. And we've licensed it all over the world. Our most recent release was 2020, and we have an online manual. So some of the things that we can do in the electrical world, Poisson's equation and continuity equations. We typically discretize the continuity equation for a variety of reasons as a gradient in the quasi-Fermi level, rather than the classic drift diffusion sort of formulation. That works better for a lot of 3.5 materials, and it's simpler to do Fermi-Dirac statistics. So those set of three equations allow us to do basic device simulation. Of course, particularly for high power 3.5 devices, we're interested in heat conduction. And we can solve not only for lattice heating, which I've written the equations for here, but also for carrier heating as well. So we can take a look at carrier overshoot and hot carrier kinds of effects by computing the average electron temperature. We are coupled into a mechanical simulator, so we can solve for elastic problems and compute the elastic strain that's present. And I'll talk a little bit about that when we go and talk about the Hall sensor work as well, because we're interested in how mechanical stress changes the Hall sensors. And then finally, we can also do diffusion and reaction equations. So for example, we've coupled vacancy and interstitial motion in capture at interfaces as part of our work on degradation and looking at how devices fail. So Alligator is a scripting language for partial differential equations. That gets parsed into an expression tree. It's assembled using finite element techniques, stored in a hierarchical parameter database. And this makes the models easily accessible and easily modified. One of the things that's really great about this is a 50-line script sets up a really complicated device simulation, and you can change the mobility model because it's right there on the command line inside that script. You don't have to learn C++, understand all of the classes that implement this, and access to all of the data that you would need. So we provide a variety of operators, all the algebraic operators that you could think of course, all the basic functions that you need, but also then a variety of things like time derivatives, gradients, Scharfeder-Gummel, if you wish to do that for drift diffusion, dot products, elastic, various vector operations. We implemented the Lorentz force that I'll discuss when we get to the Hall sensor a little bit by using a matrix manipulation on the gradient in X, Y, and Z space. So let's talk a little bit about modeling HEMT structures and using them as sensors. And in this work, I'm going to describe from Maddie Shulo and Aaron Patrick. It has been work about effectively taking a normal HEMT structure, which you see on the left with a source and a drain and a two-dimensional electron gas, very common HEMT sort of structure, but the gate's missing. And so what happens in this structure is the gate is now open to the electrolyte, and depending on the pH of the fluid that's there, it acts as a virtual gate. By trapping ions on the surface, you get different IV curves, which you can see on the right. As the pH changes, the current drain voltage relationship changes in the structure, and you get shifts, and you can use then that as a sensor. And this is done by coupling in the normal device equations for the HEMT. So we solve the Poisson and electron and hole continuity equation. But then we also solve for reactions at the interface between the hydrogen species and other ions that can be captured at that interface and their motion in the fluid and the field that's set up in the fluid. So we can do these surface reaction equations and account for the diffusion and drift of ions and hydrogen in the fluid, and then their capture upon the surface sites and changing of the charging of the surface. So when you change the pH, of course, you change the hydrogen ion population, and then that shifts the charge on the surface. So it acts like a virtual gate, and that's what gives us the sensing capability on this sensor. And this all builds on years worth of our work on modeling and understanding how AlGaN HEMTs act and perform under a variety of conditions. And being able to do this allows us to take a look at things like sensitivity. Normally for a pH sensor, you'd like to be operating at low power, but it turns out as you increase the drain voltage, you increase the sensitivity as measured in the current response per pH kind of response. So the sensitivity increases with drain bias. So if you can afford to go to a higher voltage and can afford to have a higher power in the device, if it isn't a wired application as opposed to a battery application, you can significantly change the sensitivity of the sensor and give you a little bit more. You can also do this as a function of gate length. So you can get sensitivity peaks as a function of gate length. You can see there's sort of a minimum gate length that's required to get sensitivity. At very small gate lengths, you just don't get enough charge buildup. But once you get out into about 1.5 to 2 microns, you're starting to get in the sweet spot of designing this sensor. So it gives you some feedback on several of the design parameters that you would like to have in optimizing your sensor. Now, we've also been working on Hall sensors, and Hall sensors use basically the Lorentz force. So there's a magnetic field that's applied to basically a resistor structure in and out of the plane of this device. So this is a simple two-dimensional kind of picture of what the device would look like. Plotting the electric potential here as a function of space. So again, the magnetic field is out of the screen. And because of the magnetic field being in and out of the screen, you can see the minimum kind of current path curls here, and that's due to the Lorentz force, which is indicated over here in this equation to the right. The force is the velocity of the carriers crossed with the magnetic field, so that gives a curl to the current path. And then that creates an offsetting voltage, which you can see in the colors here, top and bottom. The top contact is at a higher potential, the lower contact at a lower potential. And so this is how a Hall sensor works, is you have a 4-terminal device. You basically flow a current between 2 of the terminals and then measure the induced voltage at the other 2 terminals. And the size of that voltage tells you how much magnetic field is present. Now, one of the issues with these devices is that anything that can make the current change its path looks like an effective magnetic field. So one of the things that we've been investigating with Texas Instruments, and Thomas Weingartner has been leading this work, is to take a look at how mechanical stress can change this as well. So when one the crystal, the 6 conduction band orientations in silicon get changed. Their shape changes, and this is a basic piezo effect. You know, think about changing the tension on a string in a guitar. You get different vibrations, and the fundamental notes change. Similarly, with electrons as wave functions, if you squeeze the crystal and you make the lattice positions come closer, you change the conductivity of the electrons in those directions. And since the conduction band has these 6 channels, it ends up with creating a piezo Hall effect that looks like a current in the structure, because now the low mobility direction might be slightly different than the direction the current is flowing, which means that the current will curve and have that same exhibit. And this is what's seen actually in packaged devices. The packaged devices, or I should say before packaging, the devices have virtually no voltage offset with no magnetic field. They experience no Hall voltage, but once packaged, there's a stress paste on them from the packaging, and that actually creates a Hall offset. They have even at 0 magnetic field, they show a shift in the Hall potential, and that's what we're working with TI to understand and eliminate. So this simulation couples both mechanical effects on the electrons in a classic piezoelectric kind of effect, but also includes then the Hall effect as well. So we can couple together mechanical strain, magnetic field, and compute the changes in the device structure. So that's a short overview of some of our capabilities and some of the simulations that we've been doing recently. Again, my name is Dr. Mark Law, and if you would like to follow up with me, please contact me at mlaw@ufl.edu. And thank you very much for your attention, and I wish you to have a very good day.